this particular presentation has the goal really of reminding everybody why we're in this room today. And what I mean by that is we're a self-selected group. We didn't pick a career in technology, most of us anyway, because it was necessarily a safe career path. We picked it because it was cool and interesting and inspiring. And as young engineers or young technology enthusiasts, we wanted to change the world. And this morning we were still talking about technology. Wayne was telling stories about his days as CIO at Loomis, the armored truck company, and things they did with foam to immobilize people. If you go in someplace, you can actually, fill up the room with foam. And we were all like, wow, that's cool. This is a really interesting breakfast conversation. So my goal with this really is to remind all of us, again, why we went into technology, because most of the day you spend checking your cell phone, checking your email, dealing with personnel problems, dealing with technology that doesn't actually work the way it's supposed to, and you completely forget the fact that some of this stuff is really cool and fun and game-changing. So one of my rules of thumb whenever I present is, and I share this with anyone who asks, there's basically only 2 rules of thumb. Number 1, don't bore them. And number 2, make sure that people walk away and learn something. So I'm going to get number 2 out of the way right away now, which is, how many of you have ever heard of Godwin's Law? Anyone? Yes, thank you, John. This is for anyone who grew up on bulletin boards, electronic communication. I think a lot of you are starting to nod, and you know this law. This is the one that any conversation will inevitably devolve towards a mention of Hitler and the Nazis. And that's just the way it is, and it always gets there, and the only question is how many steps you get to take before it gets there. The guy that came up with that law is, interestingly, a lawyer by the name of Mike Godwin, and Godwin's Law kind of bounces around, and usually you can just use it when you're debating online on Facebook or whatever you're using. You can say, oh yeah, here comes Godwin's Law, because somebody said Nazis. Well, I have the distinct privilege of offering to you Godwin's second law, which is absolutely brand new because he just posted it this morning when I was prepping my slides and looking around for inspiration. And here is Godwin's second law. So this is the important thing for life that you can take away from this talk, which is this. If you have one more dragon than the other guy, you will win. So Godwin's second law, very happy with that one. So here we go. So emerging technologies, we're going to talk a little bit about past, present, and future. So here's a quote that is familiar to many of us. The past is a foreign country. They do things differently there. Those of us who have lived long enough will look back and think about, certainly the 80s were very different than the 90s, and in fact the 90s are fading off into the distance, and in fact the early 2000s were a very different country. Adding to that, one of my favorite cartoonists, if that's true, the future is a foreign country too. He is a cartoonist, a really nice guy, Zach Weinersmith, and by the way, if you do not follow his work, Saturday morning breakfast cartoons, they're really, really funny. He is a scientist. Actually, he did graduate work in science. I don't think he finished his PhD. His wife is a practicing scientist, and they're in Houston, I believe, at Rice. And he answers his email, which is awfully sweet of him. Anyway, I figured I'd go ahead and use some of his work a little later in this presentation as well. But first, I wanted to share the goal of this presentation is to give you a slight roadmap into the future. And you may be looking at this and going, that looks like a roadmap, or rather looks like a path with a compass. Why is there a kayak in it? Because that's my kayak, and that's actually a couple of miles farther down the coast. I was actually paddling at the end of a multi-day solo kayak camping expedition. But truthfully, I was looking for a slide that had a compass on it that I could actually use and had the rights to, and I figured I might as well use one of my own photographs. So there you go. That was actually earlier this year. So the compass is the path into the future, and yes, I always take a compass with me, even when I'm on a river, because they turn out to be very valuable tools. And here we go. And this is some of Zach's work. So yeah, the future is about to change beyond recognition. And by the way, for those of you who don't know his work, his protagonist is usually a bumbling redheaded guy, much like Zach himself. And the wife is always this carping woman with the blank glasses wearing a lab coat because his wife is a scientist. I don't know how she feels about this, but anyway, that's them. So what if we took everything familiar and changed it beyond recognition? Let's start with, and I'm going to walk through a couple of things. First, quantum computing. Then I'm going to talk about chaos theory and the possibility of emergence. Then we're going to talk about programmable matter and kind of put a little dusting on of man-machine interfaces just to kind of round things out. So this is where we're headed, and we're headed there much faster than you actually think. So first off, with quantum computing, I always like to start with the who, because any interesting idea, I always ask myself, how did they come up with this? Who are these people? First one who came up with quantum computing is Richard Feynman, famous physicist, one of my personal idols, and this is what he had to say about it. Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Yes, that's really how he thought. The fun problems were the ones that weren't the easy problems. And he is, of course, a Nobel laureate, or was before he died. And he's also famous, for those of you old enough to remember the Challenger crash. There was this huge, congressional inquiry. What happened? Did the rubber actually, does the rubber actually become brittle at cold temperatures? And he's the one sitting in front of all the TV cameras who said, well, let's find out, and took the rubber gasket and dropped it in a glass of ice water and demonstrated that, in fact, it did become brittle at cold temperatures, as the engineers had been trying to say. So he also laid the groundwork for quantum computing. Then there's Paul Benioff. Now, Paul Benioff is an interesting person. Many of you are going, Benioff, I know that name, I know that name. Now, you're thinking of David Benioff, who is the screenwriter for Game of Thrones, who I believe is actually related to Paul, because they all live in California. And fun fact, he is definitely related to Mark Benioff, the CEO of Salesforce, because they're cousins. So all I can tell you is the Benioff family is very, very talented. And unfortunately, Paul does not like to do quotes. He's still alive. He's in his 80s. He doesn't like to do soundbite quotes, so I had to look up and read his seminal paper, which was pretty heavy going, Quantum Mechanical Hamiltonian Models of Turing Machines, way back from 1982. The important part about this is that he showed that it was theoretically possible to do quantum computing. Other people actually had claimed that the energy consumption would be too high and it simply wasn't possible. So he's the first guy that said quantum computing is actually possible. Yuri Manin, who is actually one of my favorites because he's a polymath as well as being a mathematician, had a lot of really insightful things to say about the world as well as the mathematics behind quantum computing. But for the purposes of this presentation, I like this one. Meaning is what really matters. Mathematics can be very formal and very semantic. He focused on the meaning. And finally, let's get the show on the road. Last guy, David Deutsch. Quantum computing will be the first technology that allows useful tasks to be performed in collaboration between parallel universes. He is not making this up, and I will show you how, and it is beginning to happen, and some of the folks in this room are actually doing it. So hold tight on that. So, first question, since most of you are going, I know kind of what quantum computing is, but I don't really. I'm lucky enough to actually have studied as a particle physicist and to have trained as an engineer. So my undergraduate degree is in engineering, my graduate work was in physics. So I was really excited when the two came together in quantum computing. The basic premises we've all learned, bits are binary, they're on or off, 0 or 1. Quantum computing is, maybe they're not. They're kind of multiple states. No state is actually binary. Nothing is really quite as it seems. A photon can be both a wave and a particle. Schrodinger's cat can be both alive and dead. So you can have these states that are like on-off, or probabilistically described as being 60% off and 40% on. And you say, well, wait a minute, that actually just sounds like non-digital analog reality, but like its digital counterpart, quantum particles and qubits, quantum bits, actually behave in very distinctive fashions that have really, really interesting impacts and implications for us. So one key implication, and what most people focus on, is quantum particles can encode a lot more information. So you're packing more info into the bit or qubit. And by the way, Chris, for the sake of copy editing, I have had to go through this presentation and replace qubit, Q-B-I-T, with Q-U-B-I-T, which is the conventional spelling. But if you Google it, you can Google either and they'll both come up. So, quantum weirdness. Measurement can change the state of the particle. Simply reading it can actually change the state. So there is no such thing as actual objectivity. For those of us who pride ourselves on being scientists and engineers, this is really a pain. Because if I'm changing the value by reading it, then there's no objective reality outside me, and that's just really really twisted to think about, but it is true. It's the way the world works. There's also such a thing as quantum entanglement, which is action at a distance. Entangled particles can change each other's states even if they have nothing to do with each other. This is spooky as all get out and also real and has been demonstrated. Very cool stuff. So you can get quantum teleportation. And you're going, well, wait a minute, isn't that kind of Star Trek-y? It is, and that's actually relevant. This appears to break the speed of light barrier, but doesn't for complicated reasons that I will not bore you with. Aren't you lucky? And there's a really cool example of quantum imaging coming up. So, quantum components, you got the qubit. It's neither on or off, it's sort of offish-onish. Bell states, 2 qubits, they represent the simplest examples of quantum entanglement. For 2 qubits with 2 states, there are 4 Bell states. So the big implication here is that you've got much denser information processing than present. Most of you are going, hey, hang on, what does that do to Moore's law? You'll see that in a second. You can also do probabilistic versus exact computation of all states, which means they can be a lot faster for certain forms of problems such as AI and search, which is actually kind of interesting because they're very good at approximating things, which is what humans are great at and machines are terrible at for now. So quantum computing is not just faster, better computing, it's also different computing, as you'll see. So let's talk about what some of those implications are. Faster, better, number 1, breaks Moore's law. What is Moore's law? Some of you are thinking, I used to know what it is. Truthfully, when I put together this presentation, I could have told you that I knew what Moore's law was, and I had to go back and look it up. And the reason I had to go look it up is it talks about the density of transistors doubling every few years. What's interesting is, if you don't have transistors because you're doing quantum computing, the premise still holds, which is the density of computing processing power still doubles every 2 years, and information processing density can blast through Moore's law. That's an example of Moore's law with actual products in it. It's designed as an eye chart. You get the general idea. The key point is it ends in about 2016, and you'll notice things are already flattening out. And they're flattening out for complex reasons of manufacturing and heat and things like that. That's why you have super-cooled computers, and that's why quantum computing really makes a difference, because that flattening out is not actually flattening out anymore. It's just the pause before the really big one. Second implication, entanglement permits seeing where there actually isn't light. You're going, wait, I'm not seeing that. It's because if I have a photon in a room over here, there's light over here, but if there's a particle over there that doesn't have a photon, but I'm picking up what it's seeing, I can actually go around corners and into rooms where I am not. And I can actually see things using quantum entanglement at a distance, which is really interesting. This was from the IEEE Spectrum 2014. The picture of Gabriela Barreto Lemos is because she is the physicist who discovered this and demonstrated quantum imaging. They shine a beam of photons on an object, but instead of using those photons to form a picture, they use a completely different beam using interferometry, which I'll show you in the next slide, that has never come near the object, and that's an actual shot of that. And by the way, I put her photo up because she just doesn't look like your average image of a physicist, and I thought that was worth pointing out. So very specifically, they're using a quantum interferometer that creates a pair of, and I love how they described it, a pair of entangled photons that don't exist at the same time. They're living in a cage match. One of them wins. Only one of them can win at any given time. And by doing this observation, remember I said, when you observe it, you're actually changing its state. By doing the observation, you've killed off the other photon, which is really weird and spooky, but it works. So now you've got all kinds of new imaging that can potentially happen. But that's not the only implication of quantum computing. Then there's also, and this is the big one, it breaks many conventional cryptographic systems, RSA, Diffie-Hellman. Okay, so if you're like me, most of you are sitting here going, wait a minute, what does that do to blockchain? Because blockchain depends on cryptographic systems that are so hard to break that they might as well not be breakable. And yes, quantum computing will in fact break blockchain. So if you're deploying blockchain in your back office in order to do all sorts of cool things, and you're also planning to do quantum computing, you probably have about a 10 to 15 year window when blockchain is going to work really well, and then you're going to have to think about how you're going to handle the new quantum computing environment. The good news is quantum cryptography can also help create more secure systems using that's a whole different field that maybe next nav I'll go into quantum cryptography. So you can in fact probably do version 2.0 of your blockchain backend and have things actually work. But in the meantime, keep in mind that blockchain has a limited lifespan, thank you, quantum computing. Also, remember I mentioned that fuzziness and the fact that you can do probabilistic analysis. Well, quantum computing helps you with search algorithms separate from having more horsepower for, again, reasons I'm not going to go into at depth, but you can speed up certain search algorithms by several orders of magnitude. Again, an order of magnitude is like going from 1 to 10 to 100 to 1,000 to 10,000 to 100,000 to a million. That's fast. And so if you go a couple of orders of magnitude, you're getting from 1 to a million really fast. That does change things on how quickly you can do searches. And finally, you can simulate complex physical systems much better. So one of the great impacts of quantum computing may be that we'll actually have accurate weather predictions, which would be really awesome. Because 2 weeks ago or 3 weeks ago, I went out on a kayak paddle, and the predictions were for 60 degrees rainy and windy, and it was 65 degrees sunny and gorgeous, and we're all like, hey, it's 2019 and we still can't predict the weather, like even on the basic stuff, so that may change. So here's how IBM is using it. They developed a new approach to simulating molecules on a quantum computer that may one day revolutionize chemistry and materials science. That was in 2017. I'm happy to tell you that one day is 2019, and it is beginning to revolutionize how people are doing things, because simulations are actually the key to lots of other cool things, like I'll get to in just a second, like the concept of digital twinning, which many of you in this room are actually doing. Well, some of you in this room are doing. Digital twinning is creating a virtual simulation of the real thing. Maybe it's a ship. Maybe it's a bomber. Maybe it's a plane. Maybe it's a person. And maybe it's a biological process. And conducting virtual tests to figure out how that thing is going to perform in lots of different environments. Right now, it's almost impossible to do an effective digital twin with conventional computing because the amount of data and processing is so huge. So it's kind of the old conundrum of, if you could recreate the world exactly, you would have to have so much computing power that it's not possible to do. Well, with quantum computing, it actually is. Why would you want to do this? Well, there's value. The originals, maybe you don't actually want to blow things up to see how they perform. As my ex-husband once told me, as a young kid, he was gullible. He did not become gullible as an adult, but when he was a little kid, he asked his dad, who was an engineer, Dad, you know those signs they put on the bridges that say, weight limit, X tons? How do they figure that out? And his dad said to him, this explains a lot, his dad said, they basically load up a truck, drive it over the bridge, load it up some more, drive it over the bridge, and then when the bridge collapses, then they know what the weight-bearing capacity is. And he actually believed that, which, as I said, explains a lot, including perhaps why we're not married anymore. The other thing that's kind of cool about this is you can run experiments with your digital twins in parallel. This is a sad but very interesting technically example. My late husband, some of you know, died of cancer back in 2016. Before he died, one of the things that they tried for him, because they tried a bunch of interesting experimental processes on people, and this project is still ongoing, they essentially replicated his genetics in fruit flies, and then they bred thousands of fruit flies and hit them with lots of different chemotherapy agents to see which ones would work. Unfortunately, the fruit fly experiment was in its infancy at the time, and also it turns out that very few of the chemotherapy agents were going to work. But I know other people that were battling cancer at the same time who are still alive, thank you to that fruit fly experiment, which is a primitive model of biological twinning. It's really cool. And remember David Deutsch talking about how we're able to run multiple projects in parallel? Well, that's one of the things that twinning allows you to do. The thing is, it requires massive computational power, so that's where quantum computing kicks in. So one of the things to keep in mind, if you haven't heard the expression digital twinning before, another good takeaway, you can understand that it's a broad concept, but it has very specific applicability to a lot of different and interesting things. Last but not least, like most of the world we're living in today, this is actually literally true. PBS did a study, a show, and it was called How Star Trek Invented the Modern World. And it is literally true. The guy at Motorola who invented the cell phone saw the communicators on Star Trek and said, we could do that. And a lot of the scans, like CAT scans that are non-invasive, they were based on this idea that they had in Star Trek where you just sort of run something over somebody's body. By the way, fun fact, if you ever go to the Science Museum in Seattle, the Science Fiction Museum in Seattle, you will actually see the original thing that Bones used doing his tests, it's a salt shaker, a plastic salt shaker. It was a very low budget show. Anyway, in October 10th, 1966, they had an episode called The Evil Twin. And the premise was that Kirk somehow, there was a malfunction in the transporter, and there were two Kirks, and one was good and one was bad. Some of you actually remember this, I sure do. And what's interesting is that was the early example of a digital twin. And they spent a lot of time in the show trying to decide whether you were actually alive after you went through a transporter, because what the transporter would do was create a molecularly exact copy of you at the other end, but it would kill you first, destroy you, and then recreate you. So after the first time you went through, you didn't really exist, even though you didn't know that. Which is actually a very interesting philosophical problem that is beyond the scope of this presentation. But anyway, Star Trek was worried about digital twins back in 1966. Okay, so what's going to happen? A little timeline on quantum computing. It was pointed out to me that there's a flaw with this timeline. Perhaps you can see what it is. There's, Feynman introducing the concept in 1959, Benioff and Manin doing the mathematics in the 80s, Deutsch applying it to computing in the 90s, Yale creating the first one, and then D-Wave creating the first commercial one in 2011. Anyone see what the problem is? It stops in 2011. It doesn't go into the future. That's partly because I have absolutely no idea where it's going to go, and your guess is as good as mine. So your homework for this conference is to go think about what quantum computing might do in the future. I can tell you commercial systems are now available or in use by Google, IBM, Microsoft, NASA, Intel, the aerospace companies, a range of universities. People, this is not hypothetical. It was hypothetical in the 90s. It is real now. So we're at the dawn of a new era. So that's quantum computing. Now we're going to talk about chaos theory and emergent behavior, and there are actually links between quantum computing and chaos theory and emergent behavior. First of all, what is chaos theory? The big thing about chaos theory, which I almost studied in grad school, but somebody pointed out that they don't have very big grants for it, so I did particle physics instead because the zeros behind the grants could pay for graduate students. Chaos theory is actually, despite the name, it is non-deterministic behavior by deterministic systems. So it's not purely unpredictable behavior. It's deterministic within certain broad scope. And what I mean by that, unpredictable outcomes based on tiny shifts in initial conditions, or as Edward Lorenz, who created the Lorentz attractor, said, when the present does determine the future, but the approximate present does not approximately determine the future. In other words, small changes, very unpredictable. The pretty picture in blue and yellow is a Lorentz attractor, which essentially is a bunch of differential equations, linear differential equations that are highly predictable. The particle will appear somewhere on there, but you have absolutely no idea where on there it's going to appear in the next, in the next increment of time. And that's when you watch some of these things in 3D, it's really interesting to see them do that. These things are called strange attractors. A Lorentz attractor is a version of a strange attractor. It's a fractal dynamic. It's often, but not necessarily chaotic. So it can be chaotic, it's not necessarily chaotic. And that's an example of the Lorentz butterfly. Okay, so we talked about chaos. Now we're switching gears slightly and talking about emergent behavior. What is emergent behavior? I'll give you a concrete example of it in just a second, but I'll give you some descriptions. It's behavior of a system that doesn't depend on its individual parts. So let's say each individual part is being governed by these Lorentz equations or any other differential equations, but the things in the system are connecting with each other. And one clear example is something called a neuromodulator. The folks that are doing neuroscience about, 20 years ago, 25 years ago, came up with this concept of a connectome. And the connectome is the map of the brain. It's like where all the circuits go. As soon as we got that mapped, boom, we've got the brain. Unfortunately, it doesn't work that way. My late husband, Vladimir Brezina, looked at that and said, oops, the wiring diagram is just where you start, but the wiring diagram is in a constant state of flux because it's actually modulated by these clouds of gases or clouds of neuromodulators that are floating all around all the synapses in the nerves and that actually constitute a system of their own. So there's no such thing as a wiring diagram of the brain, anyone's brain, not even a mouse brain, not even a fruit fly brain, because the network is constantly changing, and it's changing in weird ways. And before he died, what he was studying was the simple question of why does a heart start beating? Because one day, a crab heart will just go start beating. But it didn't beat before. And how does that happen? And that is an example of emergent behavior. And the brain works that way as well. So emergent behavior is a real thing that happens in biological systems. And so when people talk about it in science fiction, they're not making it up. So what's the connection between chaos and emergent behavior? First of all, the precise knowledge of the current state isn't enough to predict the future state, either in emergent behavior or in chaos theory. And the reason for that is because at some random point, you will get the emergent behavior. Before that, there wasn't any. After that, there is, and it's a tiny change. And the behavior is roughly predictable within broad parameters. A heart is going to start beating. It's not going to start doing the mamba. And strange attractors will always make a butterfly, but you never know where on it the point is going to be. But you can't really specify it directly. And the key is not the components themselves, but the relationships within the components. So everything is connected, which is why some of the advances in networking that I'm about to talk about are kind of cool too. And out of simplicity, you get complexity. And here's an example of emergent behavior. This is known as a murmuration of starlings. I wish I had the ability to reliably do a video. Nathan was like, yeah, don't go there for this. Because there's an absolutely beautiful, if you go onto YouTube and enter murmuration of starlings, there's an absolutely beautiful sequence filmed by a couple of girls in Scotland a couple of years ago, where these vast billowing forms, we've all seen them take shape, and they set it to some beautiful music, and it gives you chills every time you look at it. But that's what it looks like, and it's incredible when you see these vast flocks of birds taking shape and doing things, and yet the birds aren't sitting there thinking about where to go, they're just behaving in an emergent fashion. So why do we care? I mean, we're technologists, birds are cool, but why do we care? Well, IoT is going to have, depending on who you ask, 50 billion devices by 2020. Do we really? The mathematical study of emergence is usually looking at distributed systems. IoT is an extreme example of a highly, highly distributed system. The real question is, do we really want our distributed computation devices to generate murmurations like starlings and to generate emergent behavior? I don't know. I'd kind of like to know that I can trust them and that doing the same thing I did yesterday is going to result in the same results that I got yesterday, but all science tells us that's probably not the case. So as we're throwing computing and processing power out there in the field, it's worth thinking about at what point does this stuff start delivering emergent behavior. And again, that's not the same thing as being intelligent. A heart isn't necessarily intelligent when it starts beating. It's just decided it's going to beat, and we don't know why. So what are some of the potential impacts here of chaos and emergence? Self-managing networks, cool stuff. For those of us who've made our careers managing networks, that's simultaneously highly threatening and highly relieving. Self-replicating systems, a little less cool, because Nathan was asking me yesterday, like, aren't you afraid of AI? And I was like, no, I'm not afraid of AI. It's when AI starts becoming self-replicating that things get a little hairy. And that's where we're kind of headed. Self-healing infrastructure, this is definitely something that's coming down the path, and particularly for cybersecurity, it's almost a necessity. We're going to have this because it's not possible to manually or in kind of a sequential fashion protect against all the threats that are out there. So here's a proper timeline that actually goes into the future. Therefore, it's not trustworthy because what is it? What's that famous quote? All models are wrong. Some models are useful. So all roadmaps are wrong, some roadmaps are useful. I would say there's still a fair amount of foundational mathematics and software development that has to happen in the emergence area. I'll hand wave and call it until 2022. Probably at least a couple of years to start commercializing this stuff, and gosh, we got at least 5 years before you got the self-replicating AIs, maybe, I hope. So. Okay, so we've talked a lot about computation and thinking and mathematics. Now let's actually get into this protean world. Does anybody remember the very first router company was called Proteus? Does anyone remember Proteus? Thank you, John. Excellent. By the way, the guy that was the brains behind Proteus was a friend of mine, and I remember calling him up some number of years after he started the company, and I was like, hey, Noel, you know what protean means? He goes, yeah, John, I kind of started a company with that name for kind of a reason. Oops. And he was actually quite a brilliant guy, still is so far as I know. Anyway, Proteus is the god of oceans, and protean means can assume multiple forms, like oceans can be frozen. Well, oceans, hopefully on this planet at least, will not boil, but you can get steam, you can get foam, you can get waves. That's the whole concept of things that can change. So Proteus is the god of oceans. So I was looking around at current developments in programmable matter, and I discovered from MIT News there's this thing called self-sculpting sand. Now, what Daniela Roos, who is the scientist, and Kyle Gilpin, who's the grad student here in this picture, are showing you are a bunch of cubes with microprocessors on it that are sort of prototypes because they're not really sand yet. But if you shrink down those microprocessors, and oh, by the way, let's remember about the computational power of quantum computing. Now you've got sand that you can put something in, a tiny model in, and it will generate a large one. So basically, if those of you remember the movie This Is Spinal Tap, they could have kind of taken the Stonehenge, put it in that, and gotten a really big Stonehenge out of it. And for those of you who don't know the movie, that's good, probably just as well. Now, one of the gotchas is as you start shrinking down processing, the problem is the networks don't shrink down replicably as they should. So there's actually a problem that as you start shrinking antennas to communicate wirelessly with these intelligent processors, you end up with heat dissipation problems and power problems, so that essentially these little processors cannot actually communicate even across very short distances at nano levels. So that's where this cool stuff comes along. Nano antennas. 2013, right in lockstep with those tiny little processors, we've got nano antennas based on graphene. And the beautiful thing about graphene is they enable electromagnetic communication in nano networks. So essentially, you actually can solve that problem with graphene-based antennas. So now you kind of start putting this all together and you say, okay, we've got quantum computing that is vastly increasing the ability to compute and is helping us solve all sorts of interesting problems that we couldn't solve before. You've got tiny, tiny processors with tiny, tiny antennas talking to each other. This is a very different world where, it reminds me of a spoof I read a really long time ago about The Lord of the Rings, and somebody said, the walls have ears, and this giant ear pops out of the wall. And, look, when you're 17, that's hilarious. But it's stuck in my head because I always thought, why aren't walls malleable? Why aren't walls, say, video screens when you want them to be? One of the things back in 2007, when we were actually doing some modeling of the internet to see whether the amount of bandwidth that was available was actually sufficient to support what was going to happen, one of the things we modeled was the idea of having a living room wall that became, at a touch, high-resolution video screens so that you could do things as a family, like have Thanksgiving dinner together without having to travel, 1,200 miles. You could just push your tables together and you could see the other people at the other end. It would be almost the same, except you couldn't pass your stuffing across to, Aunt May or whatever. But the other thing is you could just hit the button and you wouldn't have to actually be in the same room with her afterwards, which might be a benefit. Anyway, programmable intelligent matter is going to get us there. Another cool thing that came to my attention rather forcefully when I was doing research for our IoT project is this concept of bioprinting. It's actually kind of a thing that most of the folks that are worried about developing organs have thought about the fact that 3D printers can print organs. So the Weiss Institute in Harvard, for example, has developed a heart on a chip. That's a 3D printed heart on a chip. Now tie that back to emergent behavior and getting that heartbeat beating, and now you can see how all of this ties together. Jennifer Lewis, up there in the picture, she has developed microkidneys, so 3D printing of kidneys that actually work as real kidneys. And one of the guys I interviewed is actually developing 3D printed lungs for transplants. I have a college friend who has a lung transplant and has been given years of life, Lisa Tabor Connor. And the problem is you have to be taking these immunosuppressant drugs while you're while you have the transplant for the rest of your life. If you can actually print these, you're not going to necessarily react to them because they're inert. Of course, the systems that you have to tie into them are going to be somewhat bionic because they won't necessarily tie into your nervous system exactly the same way your original lungs or your original kidneys or your original heart did. But anyway, this idea of 3D printing stuff is kind of cool. Last but not least, kind of wrapping all of this up, from machine demand drones, this is not as sexy as any of the stuff that I showed you just now, but it just happened. And the reason I have this sort of odd printing is because you can see the date is April 26th, 2019. University of Maryland Medical Center transplants first drone-delivered organ. The really interesting thing is, number one, I saw this on Facebook. I didn't have to go researching this in some like scientific or technical publication. Number two, one of my friends said, oh, cool. My husband, here's a new thing for my husband. And then she put in parentheses, just so you know, he's a competitive drone racer. Like somebody was saying to me at one point, I didn't know Instagram model was a thing. I didn't know competitive drone racer was a thing. Apparently it's a thing, and now he's got a purpose for it, and he literally is applying to be part of this because you take all your skills and you save lives. Now I know the folks in the Defense Department have been thinking for a long time about drone pilots, and we're into our third generation of drone pilots, but here's a different and interesting use, life-saving drones. And last but not least of the sort of more current examples, a company called Desa.com last week announced that its engineers have this platform called Real Talk Deep Learning Platform that generates text, spoken text, that's indistinguishable from actual Joe Rogan quotes. Well, I was a little slowed down in my appreciation of this because I didn't know who Joe Rogan was. Hopefully most of you know who he is. But then after I found out who he was, I had to actually go onto the site that they had, and they said there's a bunch of places you can click to see the real Joe Rogan and the AI-generated Joe Rogan. And I thought, this is going to be easy. I mean, even if I've never heard this guy, it's AI versus a person. How hard is this? I got them almost unanimously wrong. So it's worth trying, especially if you're a Joe Rogan fan, because I can't tell the difference. I'm listening for the timbre, I'm listening for the pitch, I'm listening for the cadence, I'm listening for the word selection. Can't tell. Now, there's a catch, which is they picked Joe Rogan for a reason, because apparently he's probably got more of his voice recorded in the internet than anyone else ever in the history of humanity. So they had an infinite amount of data to tune this AI, this machine learning from. But okay, that's generation 1.0. As it gets better and better, there's going to be more and more of this. And Robin and I will be talking a little bit on Wednesday about AI and where it's headed from an IT perspective. So I didn't spend a lot of time in this presentation digging into it. But the fact that we've got fake Joe Rogan out there, this is also a reason why I no longer write science fiction for a living, because some of my friends who are still writers say things like, you used to write science fiction? Yes, I sold a novel and I sold a short story, but I'm a terrible science fiction writer. Why? Because my time scales are off. Back in the early 1990s, I wrote a couple of short stories. One of them started with a guy that walks into his apartment and he's really sad because he can't play his movies or listen to his music or read any of his books because they're all in the cloud. 1990s, not too bad, pretty forward-looking. Now, Jeff Bezos was having the same idea and started Amazon. My problem was I said it in 2050 with a 50, not 2015. So this is kind of why I don't write science fiction. But I also came up with this idea that in the future there would be effectively fake news, because you could have videos and you could have a video of a person speaking and you would not know that that person had never said that thing, and you could start a war. Or start a religious schism or something like that, because the Pope never said that, did he? Yes, he did. Here's the video. You can hear it. And of course, now that's all actually happening. And in fact, Salome and I were at an event last week, and they did this kind of fun thing where they made us work for our lunch. So we all went to the buffet, got our lunch, and sat down. They said, okay, now each table has to come up with the prediction that's going to happen in the next 5 years. We're going to save this in a time capsule. We're going to bring it out 5 years from now. Well, we were hanging out with some really interesting people, and we just wanted to talk to them. So we kind of looked around and chatted a bit, and then I was like, you know what? Within the next 5 years, the first AI actor or actress will have a mainstream role in a mainstream movie. Fake person, doesn't exist, looks real, sounds real. We don't even know this person isn't a human. That's our prediction. Great, let's have some more chicken. So that's what we did. And that is happening. And that was before I found out about Joe Rogan. Tying all the way back to the foreign country of the future that we talked about, that Zach Weinersmith talked about, if you think about quantum computing, emergence, self-organizing materials in chaos, nanocommunications, bioprinting, human-machine integration, and AI, which we barely touched on, the future is going to be a really, really weird place. And as his wife said, what if we took everything we know and changed every single thing? And that's kind of what's going to happen. That said, I'm going to wrap up with two more things. One is I've actually brought my props, which I'll share with you in a second. But also, I just find this incredibly poignant, this poem by Yuri Manin, who is the mathematician that came up with quantum computing. He's now 82. And he wrote this poem that really talks about the brevity of life and the way your perspective changes. And there's a pun inherent in the title, Space-Time as Diagnosis, Intercostal Nostalgia. Intercostal nostalgia is a play on words for intercostal neuralgia. Intercostal are the muscles that connect your ribs. Intercostal neuralgia is a sharp pain in your chest. Your chest is hurting. And there's various reasons for it, but he replaced neuralgia with nostalgia and talked about longing for time when I was longing for space. Long ago when he was young, space was closed. Now, space is open. He has this vision of the future. But time is almost closed. He's 82. We all don't know how long we have. We should spend it looking at that open space and exploring that open space. And that's really what I hope you get out of this presentation. So, before I end entirely, because I don't want people to start thinking, God, that was really uplifting, except the part about dying at the end. I wanted to wrap up with my my props. A couple of books that I have found always uplifting and inspiring. First of all, Soonish, which is Zach Weiner-Smith's book with his wife. It is the emerging technologies that'll improve or ruin everything, and it really is. I actually didn't crib nearly as much from this book as I thought I might, because I'm just so interested in everything out there, but he does a fabulous job synopsizing things, plus, you really can't argue with this, he's got cartoons, and they're funny cartoons, so when you read the book, it's actually very entertaining. Obviously, there's a theme here, because the other great book that I love and is greatly mind-expanding is What If by Randall Munroe. Those of you who are going, Randall who? XKCD, the cartoon, the little stick figures that do really funny things. Yeah, he wrote a book too, and his book is hilarious because he takes scientific and mathematical and logical explanations of extremely weird problems that people just randomly send him. So one we were talking about yesterday while we were prepping was what would happen if everybody in the Earth got together and jumped up and down at the same time? Now, the truth is, nothing would happen because the relative mass of all the people and the Earth is just, it would be like a flea jumping on you, only less. It just has no impact. But the way he maps it out is so funny. He says, let's say all the 8 billion people of the world got together. Well, they could stand in a place about the size of Rhode Island. But heck, let's not make it a hypothetical place the size of Rhode Island. Let's make it Rhode Island. And he takes it from there. And so now there's this mass of people standing around Rhode Island realizing they can't talk to each other because they've come from all the different continents. And it goes on, and it's hilarious. Anyway, even though it does end in world devastation because everybody's in Rhode Island and they can't get out because you can't, 8 billion people overwhelm the capacity of the very small airport that's in Rhode Island, not to mention I-95. Anyway, it keeps going. You get the idea. These are great books. So as you continue exploring that open space that Yuri Manin talks about while time is slowly closing, you might want to consider these books. I have nothing to do with the authors. I just think they're cool. And with that, thank you very much.